Picture this. Someone in your family overate at dinner and is complaining of a bad stomach ache from acidity. You look in the kitchen, you've got lemon juice, vinegar, and baking soda. Which one do you give them to actually fix the problem? To answer that, we need to look at the chemistry of our food. Let's start with acids. If you've ever bitten into a raw lemon, you know the physical signature of an acid. It tastes sharp and sour. Bases sit on the opposite end of the spectrum. They have a distinctly bitter taste, and if you rub them between your fingers, they feel slippery and soapy. This chart shows the baseline litmus paper rules for identifying these chemicals. Acids turn blue litmus paper red, while bases turn red litmus paper blue. Understanding these fundamental chemical properties is the only way we can figure out our stomachache problem. We have to know exactly what kind of substance we are dealing with before we can neutralize it. In a laboratory setting, you can't rely on taste or touch. Ingesting an unknown chemical can cause severe harm. That's why chemists use specific substances called indicators to safely identify what's in a test tube. Some of the most reliable tools come straight from nature. These are called natural indicators. Litmus, for example, is actually a purple dye extracted from a plant called lichen. You probably have another natural indicator sitting in your kitchen cabinet right now, turmeric. While it is commonly used to flavor food, it also serves as a chemical sensor that reacts visibly to pH shifts. This diagram shows turmeric's color shift across a simulated pH scale. If you've ever dropped curry on a white shirt and tried to scrub it with soap, you've run a chemical test. Soap is a base. When the yellow turmeric hits that basic soap, it immediately undergoes a reaction and turns a dark reddish brown. This reaction is reversible. By rinsing the cloth with plenty of water, you wash away the basic soap, and the stain shifts back to its original yellow. Natural indicators give us a reliable, highly visual method to detect basic compounds in our environment, completely removing the need to come into direct physical contact with them. Nature provides great tools, but modern labs require manufactured precision. This is where synthetic indicators, like phenolphthalein and methyl orange, come in. This is a test of phenolphthaleine's reaction. When you drop it into an acidic solution, it remains completely colorless. But add it to a base, and the entire solution turns a vibrant pink. Methyl orange has different rules. Introduce it to an acid, and it turns a sharp red. Put it in a base, and it changes to yellow. Let's test this out. If you take that baking soda from earlier, which is a base, and add a drop of phenolphthalein to it, what color will the mixture turn? It turns pink. Committing these specific color shifts to memory is essential. You need these rules locked in to correctly analyze lab samples and pass your chemistry exams. We've focused entirely on color so far, but some chemical reactions bypass sight completely and target your sense of smell. These are called olfactory indicators. This diagram lists the 3 specific examples you need to know for your exam: onion, vanilla essence, and clove oil. The first rule of olfactory indicators deals with acids. If you place any of these 3 substances into an acidic medium, like hydrochloric acid, the mixture retains its characteristic scent. The acid doesn't destroy the odor. However, if you mix them into a basic medium, like sodium hydroxide, the reaction wipes out the odor entirely. The smell is completely destroyed. Chemical interactions can alter a substance's scent with the same precision as its color. Olfactory indicators provide a specific way to test for basic compounds without relying on sight. Now, let's solve the problem we started with. The acidity causing that stomachache is exactly what it sounds like, an overproduction of hydrochloric acid inside the stomach. If you chose lemon juice or vinegar as the remedy, you'd actually make the pain worse. Both of those are sour-tasting acids, which means you're just adding more acid to an already acidic environment. The correct choice is baking soda. Because it is a mild base, it reacts directly with the excess stomach acid. The 2 chemicals cancel each other out, undergoing a process called neutralization to force the stomach back to a neutral, painless state. To help you keep all these interactions straight, pause the video right now and take a screenshot of this table. This is your master cheat sheet for every indicator rule we've covered. Categorizing these substances and mapping out how acids and bases interact allows us to master the chemical balances that govern our own bodies. Acids and bases are intuitive chemical opposites, one sour, the other bitter. Yet when exposed to reactive metals, both triggers the same violent reaction. This establishes a foundational rule of chemical properties. Combining an acid with a metal reliably yields a salt and hydrogen gas. Consider zinc and sulfuric acid. Acid plus metal yields salt plus hydrogen gas. On a molecular level, the zinc atom physically displaces hydrogen from the acid, taking its place to form the metallic salt, while the isolated hydrogen escapes as a gas. This gas is easily identified using a flame. When the escaping hydrogen ignites, it produces a distinct pop, confirming the reaction has taken place. Strong bases also react with metals to produce hydrogen gas, though the resulting salt structures are significantly more complex. In a reaction between sodium hydroxide and zinc, we see the formation of sodium zincate. Because this complex salt appears frequently in advanced chemistry, recognizing its specific formula is vital. Unlike the universal reactions seen with acids, this base-metal interaction is selective and does not occur with every metal. Whether starting with an acid or a strong base, the introduction of a reactive metal forces a structural breakdown. The process liberates hydrogen and permanently alters the original chemical into a new metallic salt. A second major rule applies to metal carbonates and hydrogen carbonates. Reacting these compounds with an acid consistently produces a salt, water, and carbon dioxide gas. We observe this by adding hydrochloric acid to sodium carbonate. The reaction results in sodium chloride, water, and carbon dioxide. To prove carbon dioxide is present, we pass the gas through lime water. The reaction creates calcium carbonate, appearing as a milky white precipitate. If the flow of carbon dioxide continues, the milky appearance will eventually vanish. The excess gas and water react with the solid calcium carbonate to form calcium hydrogen carbonate. Because this new compound is fully soluble, the precipitate dissolves and the liquid clears. Identifying the gas requires observing this entire sequence. The initial precipitation confirms carbon dioxide exists, while the subsequent clearing defines the transition from a carbonate suspension to a soluble bicarbonate. The most direct interaction occurs during neutralization, where an acid and a base cancel each other's effects to yield only salt and water. This is demonstrated by mixing sodium hydroxide with hydrochloric acid. The base and acid neutralize one another, producing sodium chloride and water. This rule allows us to classify materials that aren't obviously basic, such as metallic oxides. Consider copper oxide reacting with acid. When black copper oxide dissolves in hydrochloric acid, it creates a blue-green solution. The resulting products are copper chloride and water. By applying the neutralization template to these products, we can verify the nature of the oxide. Because metallic oxides react with acids to produce salt and water, they are basic oxides. Conversely, non-metallic oxides react with bases in the same manner, making them acidic. The acidic or basic nature of any oxide becomes clear simply by tracking whether the reaction results in the characteristic salt and water of neutralization. These 4 rules provide a complete framework for predicting chemical properties. We can now use these templates to solve applied problems. For example, acidic curd reacts with copper vessels, creating toxic salts. We also use these rules for deduction. If a compound produces effervescence and extinguishes a flame, it's carbon dioxide. Our framework shows only a carbonate would produce this. If we then find that the resulting salt is calcium chloride, we can conclude the original compound was calcium carbonate. Predicting chemical reactions is a matter of applying these overarching structural patterns to new scenarios. Memorizing isolated equations is inefficient. Mastering these 4 structural frameworks provides the ability to accurately predict the outcome of almost any standard chemical reaction. We have 2 identical setups here. The beaker on the left holds hydrochloric acid, and the bulb is glowing brightly. The beaker on the right holds sweet glucose water, and the bulb is completely dark. To conduct electricity, a liquid needs a pathway of free-floating charged particles, or ions. The glowing bulb proves the acid is full of these active ions carrying the current, while the glucose remains as neutral, intact molecules. When an acid molecule like HCl drops into water, it splits apart. It releases a hydrogen ion, which immediately attaches to a water molecule to form a hydronium ion. That specific particle is the defining feature of an acid. Bases work differently. When a base like sodium hydroxide dissolves, it splits and releases a hydroxide ion. The universal rule is simple. An acid is any substance that produces hydronium ions in water, and a base is any substance that produces hydroxide ions. Let's test that rule. If we blow dry HCl gas over dry blue litmus paper, the paper stays blue. But if we blow that exact same gas over wet litmus paper, turning it instantly red. Without water to accept the hydrogen ion, the acid molecules cannot break apart. The water molecules actively catch those hydrogen ions out of the gas. Water is strictly essential for acidic properties to manifest. This diagram shows the pH scale. It is the standardized tool we use to measure the specific concentration of those active hydrogen ions. Notice the shape of the red wedge. As the concentration of hydrogen ions increases, the pH number drops. Sliding down toward 0 means the solution is getting more crowded with hydrogen ions. This chart above the scale compares two acids. If we drop 10 molecules of a strong acid into water, all 10 split apart into active ions. If we drop 10 molecules of a weak acid, only one might actually split. Chemical strength is a measure of molecular dissociation efficiency. The pH number maps directly to the physical density of the ions that successfully broke apart in the solution. When rain absorbs atmospheric pollutants, its pH drops below 5.6. The resulting excess hydrogen ions react directly with calcium carbonate. Over time, those extra ions dissolve the solid features of this stone statue. This graph plots the pH of the human mouth over time. Bacteria produce acids by breaking down leftover food. When the line crosses below 5.5, the acid concentration is high enough to start dissolving the calcium phosphate in your tooth enamel. Pause the video and test your understanding with two questions. First, comparing a solution at pH 6 to one at pH 8, which has a higher hydrogen ion concentration? Second, do basic solutions contain hydrogen ions at all? Because the scale is inverse, pH 6 has a higher concentration of hydrogen ions than pH 8. And yes, basic solutions do contain hydrogen ions. They are simply vastly outnumbered by the swarm of hydroxide ions. Plants require a specific pH range to grow properly. If a soil gauge reads a highly acidic pH, 4, a farmer can treat the field by sprinkling a base, like quicklime, over the top layer. The added base introduces hydroxide ions, which seek out the excess hydrogen ions in the soil. When they collide, they fuse together into neutral water droplets. This removes the active acid, and the soil gauge rises back to 7. We can distill all of this into 3 rules. 1. Acids produce hydronium ions. Bases produce hydroxide ions. 2. A lower pH number indicates a higher concentration of hydrogen ions. 3. In neutralization, those two ions combine to form water. Mastering this topic means understanding that everyday events, from treating agricultural soil to digesting a meal, are driven by an invisible, microscopic tug-of-war between these two simple ions. In 1930, Mahatma Gandhi led thousands on the Dandi March to protest a colonial tax. The focal point of that massive demonstration was a simple chemical compound, sodium chloride. Today, we harvest this same compound in massive outdoor pans to serve as the primary raw material for a multi-billion-dollar chemical industry. To understand how one compound drives so much production, we have to look at its chemical family tree. Salts are categorized based on shared positive or negative radicals. Notice how sodium chloride and potassium chloride both fall into the chloride family, while sodium chloride and sodium sulfate group together in the sodium family. Mapping these radicals allows us to organize thousands of different salts by their shared properties, providing a structured way to predict their chemical behavior. While it is easy to assume that every salt is perfectly neutral, many compounds in these families do not have a pH of 7. Think of salt formation as a chemical tug-of-war. A salt's final pH is determined by the relative strengths of its parent acid and parent base. Matching a strong acid with a strong base causes the forces to cancel out completely. The result is a neutral salt, like sodium chloride, sitting perfectly at pH 7. If a strong acid overpowers a weak base, the tug-of-war becomes one-sided. The resulting salt, such as ammonium chloride, pulls the indicator into the acidic zone, dropping its pH below 7. Let's test this rule. Sodium acetate is formed from acetic acid, which is weak, and sodium hydroxide, which is strong. Where will the pH land? Because the base is stronger, sodium acetate is basic, pulling the pH above 7. Understanding these underlying components allows us to scale production industrially. By passing electricity through brine, an aqueous solution of sodium chloride, we trigger the chlor-alkali process. Here, the salt and water molecules split to yield sodium hydroxide, chlorine gas, and hydrogen gas. Mastering the pH balance and identifying these base components is the first step toward unlocking the industrial potential of simple brine. We can now look at 3 major salt derivatives. First is bleaching powder, formed by passing chlorine gas over dry slaked lime. Its chemical formula is CaClO2, and it is used extensively to bleach cotton in the textile industry and to disinfect drinking water. Next, we have the carbonates. On the left, we build baking soda, or sodium hydrogen carbonate. On the right is washing soda, which is sodium carbonate bonded to exactly 10 water molecules. Baking soda is versatile because it releases carbon dioxide when heated or mixed with an acid. This makes it a primary active ingredient in fire extinguishers, like this vintage metal model, as well as an antacid for indigestion. Note this distinction. Baking soda is the pure chemical compound sodium hydrogen carbonate. Baking powder is a mixture of baking soda and a mild edible acid, like tartaric acid. The 10 water molecules attached to washing soda represent the water of crystallization. Many salt crystals appear dry to the touch, but chemically harbor a fixed number of water molecules locked within their structure. Our third major compound relies on this concept. When gypsum is heated to 373 Kelvin, it loses water molecules to become plaster of Paris. Its formula, calcium sulfate hemihydrate, indicates that 2 units of calcium sulfate share a single water molecule as a structural bridge. If plaster of Paris is exposed to moisture, it absorbs 1.5 molecules of water back into its structure, locking it into a solid, rigid mass of gypsum. Whether putting out a grease fire, making bread rise, or casting a broken bone, a salt's utility is dictated by its precise chemical structure, down to half a water molecule. Let's lock in the most heavily tested concepts from this topic with a rapid-fire review. First, what is the common name for CaClO2? And which specific salt is used to permanently soften hard water? CaClO2 is bleaching powder, and hard water is treated with washing soda. Next, what is the exact physical result of mixing plaster of Paris with water? It crystallizes back into a hard, solid mass of gypsum. Finally, why must plaster of Paris be stored in a moisture-proof container? Because ambient humidity triggers the gypsum reaction, rendering the powder useless. Save this reference grid. Tracking the movement of atoms across these specific reactions provides the final link between raw brine and the complex industrial salts we have covered. If someone in your family overeats and develops a burning stomachache, your choice of remedy is a chemical one. You wouldn't hand them lemon juice or vinegar. You'd reach for a baking soda solution or an antacid. That choice relies on the fact that acids and bases can nullify each other's effects. Generally, acids are sour and turn blue litmus paper red, while bases are bitter, feel soapy, and turn red litmus paper blue. To test these properties safely, we use indicators like Litmus, a purple dye extracted from lichens. These organisms have been cataloged in botanical studies for centuries because of this specific chemical utility. You can observe these indicators in daily life. If a yellow curry stain on a white cloth is scrubbed with basic soap, the turmeric in the stain reacts, turning the fabric a deep reddish brown. These color shifts provide immediate data. They allow us to identify the nature of a substance and predict its behavior without the danger of tasting unknown chemicals. Instead of memorizing individual equations, we can use templates to predict outcomes. For instance, an acid reacting with a metal always produces a salt and hydrogen gas. You can confirm this when the trapped gas ignites with a characteristic pop sound. When an acid reacts with a metal carbonate, the result is a salt, water, and carbon dioxide. We verify the gas by passing it through lime water. If the clear liquid turns milky, carbon dioxide is present. Apply the template. If you mix sodium hydrogen carbonate with hydrochloric acid, what products will form? You get sodium chloride, water, and carbon dioxide. This predictability even applies to metallic oxides. Because they react with acids to produce salt and water, we classify them as basic oxides. These templates function as a shorthand for chemical logic. Once you know the general rules for how these groups interact, you can accurately construct the specific equations for almost any pairing. However, these reactions require a specific environment. Dry hydrogen chloride gas will not change the color of dry litmus paper. The acidic character only appears when the substance is in an aqueous solution. Hydrogen ions cannot exist alone in a solution. They exist only after combining with water molecules to form hydromium ions, or H3O+. Water is what allows these ions to dissociate and become chemically active. Because this interaction is highly exothermic, mixing them requires caution. Pouring water into concentrated acid can generate enough heat to cause the mixture to splash out or shatter the glass container. The safe protocol is to add acid slowly to water while stirring. This allows the heat to dissipate through the larger volume of water, keeping the temperature manageable and the reaction controlled. Water acts as the essential medium that enables ion separation. While it is necessary to activate the chemistry of acids and bases, the speed of that interaction must be carefully regulated to prevent a dangerous release of energy. To measure the strength of these solutions precisely, we use the pH scale. By using a universal indicator, we can see a spectrum of colors that correspond to the exact concentration of hydrogen ions present. On this scale, 7 is neutral. As the pH drops toward 0, the concentration of hydronium ions increases. As it rises toward 14, the concentration of hydroxide ions increases, marking a stronger base. This balance affects entire ecosystems. When the pH of rain falls below 5.6, it becomes acid rain. This low pH water flows into rivers, making survival difficult for aquatic life and slowly dissolving the calcium carbonate in stone structures. These reactions occur beyond Earth as well. The atmosphere of Venus is dominated by thick clouds of concentrated sulfuric acid, proving that these chemical principles remain constant across different planetary environments. Whether analyzing a distant planet or a laboratory sample, your reaction templates remain the same. Metals, carbonates, and oxides each follow a specific path when they meet an acid or a base. From the digestive processes in our own bodies to the corrosive weather of our neighbors in the solar system, these rules allow us to predict and understand the behavior of the world. By mastering the pH scale and reaction templates, you can analyze the chemical interactions that shape the environment around you.